Welcome to the 11th class meeting of the Introduction to DSP. We will have homework assigned and will be due on next Tuesday. And also we will have the first exam on next Wednesday from 7 to 11 p.m. here in LG 102. It takes up around 20% of the entire course requirement. Here goes the overview of our course. We are basically still reviewing the materials, not intensively, but covered in signal-gen systems in the part of the discrete time signal processing. So today we are going to finish the Z-transform part and moving toward the sampling theorem and theory and analysis of sampling. So probably chapter 4 will be almost included in the coverage of the midterm. Here goes the messages I've told you so far. First one is that whenever you try to remember something that is written in equation form or in theorem lemma definition form, always try to verbally express or state mathematical results. Like when you have a discrete time convolution, which is convolution sum, that is the multiplication of two discrete time signals, then the Fourier transform becomes what? Becomes circular convolution of these two signals. Am I right? Oh, something's wrong. Yeah, something, just a second. Yeah, I believe this is correct. Something like this. So, like multiplication in time domain becomes circular convolution in the frequency domain, something like that. That is the verbal expression of mathematical theorem or definition. And the second one is that sometimes the hallucination of your favorite LLMs gives you completely opposite results, like in the square root raised cosine per shaping of digital signals. When the Rho factor increases, the bandwidth also increases, so the output signal variation increases because you have larger bandwidth. The problem is that sometimes your LLMs gives you the opposite answer, as you've checked from my grading of your one of the MATLAB homework problem, right? So be careful when you do your midterm exam and final exam too. I'm kind of thinking about not allowing the use of LLM during the midterm exam, even though everything else is open. So you can access the web pages, you can access the textbook, any textbook available, but no LLMs, something like that. Okay, here goes the review. We've covered part of section 3.2, 3.3, 3.4, and a little bit covered 3.5, which is the last section of chapter 3. The first thing was alarming signal quotient. So let me rephrase this first alarm. Probably you remember from your high school math, something like this. Suppose you have two sequences. So let me use your familiar notation for two sequences, A and B. Here, n is the sequence index. In this DSP course, we may interpret that as a time parameter. Now, we know that these two sequences have its own limit. Here, A and B are finite, real numbers. Sometimes this notation means they are finite, not positive or negative infinity. Now, this is given. And you have theorems. First, what was your theorem? Probably you remember this one. Right? And you had other results, which is not used here right now, but you've seen something like this from your favorite 수학의 정석. One of the pages has that one, that table. You remember? So suppose you have two sequences, both convergent. Then some sequence. So you construct the new sequence whose nth term defined as the summation of the nth terms. Now, what is the limit of this C sequence? That is answered, that question is answered in this first result. Got it? So if you have two convergent sequences and you construct the new sequence, that is the summation of the terms. Then this one says what? The new sequence converges. And its limit is the sum of the limits. Got it? So limit of some sequences is the summation of the limits. That is what I told you. Verbally state mathematical results. Do not try to just remember this. Try to interpret verbally, then the results comes more close to you. So whenever you see something, try to verbalize. Try to use ordinary or technical terms. Got it? Now, this is very useful in our understanding of some of the results related to the some strange behavior of region of convergence. So here we have a x1 discrete time sequence signal, x2 discrete time signal, and we construct a new signal. So story is very similar, right? You have two sequences and construct a new signal. Similarly, you have two discrete time signals. Check how they differ. And each one has its Z transform with region of convergence R1 and R2. Now be careful. The difference between these two is very subtle and important. Here we have only one sequence, right? AN, and here is another sequence. Now let me ask you, how many sequences when you construct this function of Z? Actually, from a single signal, you have what? You have to consider infinitely many series. Series is a special case of sequence, right? Suppose in your high school, you have a sequence, 수열, and you sum up to the kth term, and you construct a new sequence, but this is usually called what? Series, right? sequence and series. Recall the definition of Z transform, what it is. It is a series, right? However, by changing the value of Z, you have different series. You have different series. Some series converges. Some series does not. This ROC, that is a subset of the entire imaginary complex plane. So this is the set of all complex numbers. On this set, you have convergence of this infinite series. When you take Z from this set, for X2, the same. You have possibly test infinitely many series with different values of Z, and for some value of Z in this set, you have convergence. Now, our previous results was something like this. Now you consider, is it A and B? Okay. You consider a linear combination of two signals to define the third signal. Got it? So this is a general version of that one, right? By the way, what was the second result in your high school study aid book, 수학의 정석? I'm not sure whether this was the first one or that was the first one, but I remember something like this. Got it? So if you scale, then the limit scales. Got it? So if you combine these two, actually, what does that mean? Limit of linear combinations of two sequences is the linear combination of the two limits. That is the verbal expression of this result. So you have a linear combination of two sequences, x1 and x2. So you have x3. Now, what is the definition of the Z transform of x3? You have a series. If you change the value of Z, a complex number, you have different series. Now, we don't know exactly where. What is the necessary and sufficient condition for this series converge? However, we know from our theorem, this theorem, got it? On the intersection of two reasons of convergences, since this one converges and that one also converges, this must be equal to the summation of these two on this set. Got it? So it is guaranteed that on the intersection of two reasons of convergences, your new discrete time signal, that is a linear combination of two sequences, two discrete signals, converges. However, we don't know whether the actual reason of convergence is bigger or equal to this one. We don't know. That's why our result from the textbook said what? Contains the intersection. Got it? And similarly, you have other results, very similarly. So your high school math is still very, very useful. Okay, so that was the most important one. And this observation directly gives us then when the region of convergence increases is bigger than the intersection. And most of the cases, not always, but most of the cases, it is because pole zero cancellation occurs. So it's like, suppose this is some rational function of z. And this is also another rational function of z. By the way, I emphasized again and again and again that not every discrete time signal gives you rational function of z as your z transform. However, some useful discrete time signals gives you rational function of z as its z transform. Never forget this, got it? Because since I didn't have enough emphasis on this fact, I suffered for more than 5 or 6 years, even up to almost the end of my PhD. Got it? So very important. Anyway, so you have two expressions. And when you sum up two rational functions of z, sometimes after you have the common denominator and you sort out the numerator, and if you factorize these two, sometimes a pole that is a root of the denominator polynomial, and you have the same 0 in the numerator polynomial. So if z is so you are very tempted to cancel them. However, whenever you cancel some factor in the numerator and denominator, you must check whether it's 0 or not. If it is not 0, you can cancel. And then what happens? Usually, the region of convergence increases. Why? Because your new sequence gives you that one. And we've seen something interesting, not only here, but we will see in the section 3.5. So you have some discrete time LTI system, and you apply a discrete time signal. And here you have the output. Sometimes its Z transform has pole somewhere, but its Z transform of the, capital H, input exactly cancels the pole. And you may say that, so what? But what is important is that in order to obtain the output Z transform, you need to first convolve these two signals. And that convolution itself removes that pole in the Z transform of the system. You will see anyway. So what you need to remember is pole zero cancellation. You must be very, very careful. Okay, what else? Yeah, I will skip that. So here goes the preview or review, because we just a little bit covered section 3.5 in the last class meeting. So here goes another alarming sound, caution. Not every DT LTI system has . as I told you, some people have very wide sense, 광의의 넓은 의미의 definition on the linear constant coefficient difference equation. So they may have infinite terms, infinite summation. However, as I told you, most of the people don't accept that one, but has narrow sense, 협의의 definition on LCCDE. So if it's confusing, I will like this one. So finite means finite term, LCCDE. Got it? So here, what I'm saying is that when you are given a discrete time LTI system with possibly impulse response h of n, you cannot find an LCCDE that describes the input-output relation. Got it? So LCCDE has limitation. However, as I repeatedly told you, LCCDE is very, very powerful tool because it describes some behavior or relation between two signals or sometimes three signals because it's related to the input and impulse response and output. So it kind of handles dynamical, time varying something or time function. But as we will see today, if we apply Z transform, it converts to an algebraic equation. And as you know in algebra, 대수학, you just find sometimes roots of some polynomial and you are happy. Quadratic, sometimes higher order. And you do actually exactly the same thing here. So difference equation is related to a dynamical system, but you have an algebraic equation that seemingly does not relate to the time varying something. This is the power of connecting two mathematical areas. As I emphasized already, and as you learned in linear algebra, some differential equations have almost the same thing. And now you know that those differential equations were what? Described by linear constant coefficient differential equation. The kind of input-output relation was described in this way. And when you applied Laplace transform, you had almost the same thing. So differential equation turns into an algebraic equation where you used S instead of Z here. As you remember, in Laplace transform, we introduce a complex variable S. And here in the Z transform, we introduce the complex variable Z. Anyway, so how many of you enjoyed this Fibonacci sequence problem? Probably from that recurrence formula, original recurrence formula, probably you constructed an LCCDE. And as I have given you in some early homework, you constructed the input signal that has delta of n and delta of n minus 1. So your input is something like boop, boop, and all 0. And then this discrete time system with initial rest generates the Fibonacci sequence. That was one of the MATLAB homework, and you plot it. And I asked you to look up the Wikipedia to find the general formula for Fibonacci sequence that had what? 2 base raised to the power of n times some constant, and they were linearly combined. And at that time, probably you wondered how we can find this base of the exponential function. And some of you, I hope everybody, now already knows how to do that. The key is what? The key is to find the Z transform of the output sequence, that is Fibonacci sequence, and then find what? And then find the root of the denominator. And then you apply partial fraction expansion so that you have two terms. Then you apply inverse Z transform to have what? Two linear combination of two exponential functions. Okay, why your faces are saying that? Did we have that homework problem? Did I miss something? Today is not the due for that homework. Okay, probably I'm hallucinating. Let me find the okay, and wiki. By the way, Wikipedia is one of the most powerful resource for your study. When I was a middle school student, one day, some delivery persons brought a very heavy series of books called Junior Encyclopedia of Britannica. Britannica 청소년 백과사전. And still I have it actually. I didn't yet thrown away. And it kind of contributes to the instability of the faculty apartment because it's very heavy. At that time, it was not easy to have encyclopedia. And encyclopedia, the publisher of an encyclopedia usually went bankrupt. You don't know the history of Korean publishers, but there were very successful publisher called 태극 문화사. Probably nobody knows. Even your father and mother does not know because I'm at the age of your father and mother, and when I asked this story, they never knew. Anyway, in Korea there were 태극 문화사, and they published their own encyclopedia, asking a lot of experts in every area of academia. Like, for example, if they wanted to have some explanation about communications, then they found some professor in communications and asked them to write some small article about, for example, Fourier transform and its application to digital communication. And they write. And of course, they don't do free. So the publisher gives the kind of rewards. So publishing an encyclopedia, just getting the manuscript was very, very expensive. Second one is that, so it kind of contains all the knowledge of current at that time. So you have to have around more than 30 or up to 50 volumes. And that requires a lot of typesetting experts. There was no laser printing at that time. We really had 활자, the live typeset. So if you go to the imaginary some copy shop, then they had so-called typesetter, 식자공. And they had a case with every possible character and even Chinese characters, because at that time we intensively used Chinese characters. Anyway, and from the invention of the internet, this very expensive but important business got challenged. And now we have Wikipedia. And the Britannica Encyclopedia, that publisher, bankrupt long ago, even in, I remember, 1990s. Interestingly, the manuscript can be updated by any person, but if some information is not correct, they have voting system. So this information is, of course, very old or important, but old knowledges are very, very refined version. And whenever you have any question, type keyword and also wiki. Then your browser will direct you to Wikipedia. Anyway, this includes almost every possible knowledge related to Fibonacci sequence. And as you've seen, by the way, sometimes we start from 0, sometimes we start from 1, depending on the choice. But you see here, difference equation. Of course, in our term, in this DSP, we have to define output Y and some input. You can do that. And the idea, you may say that this is output Y. And after Z transform, where it is? Did I skip something? Yeah, this is a general form. So you can find that your Z transform of the output have two rational functions. Each of them have pole here and there. So you have this Z transform. Right? Basically, you use that result twice to get the general form. So please, 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 even though you haven't completed this homework, do it for your midterm exam. Got it? You may see some page, surprisingly, some page from 수학의 정석, and I will ask you to solve it by using Z transform. And you may say that, hey, do you have 수학의 정석? Actually, I have my version of 수학의 정석. Still, I have it, published in 1986. You may not believe, but let me show you. Anyway, so this will be quickly covered, and then we are going to move to sampling. By the way, some professors or lecturers start from sampling for this DSP course, but I don't like that idea because discrete time signal is a mathematical model we handle here. And there are, in nature, some signal in discrete time. And also, there are some discrete time signals, which is mathematical model. That signal, that discrete time signal, is just used to model some continuous time signals. Sometimes, in order to have the discrete time signal, we use the procedure called periodic sampling or uniform sampling. But you have to remember this one. Not every, today I'm using this, not every, a lot of times, not every discrete time signals is obtained by sampling a continuous time signal. We have, you will see, we have some physical thing that in nature, we have to use discrete time signal model. Got it? So be careful. Anyway, so here, as I once told you, uniform sampling and scalar quantization is the key, even though the emphasis is not on this scalar quantization. However, for real world digital signal processing, after uniform sampling or periodic sampling, you have this scalar quantizer, and even you have binary encoder. But in this course entitled Digital Signal Processing, actually this course is about discrete time signal processing. So we just focus on this one and study a lot in the time domain and in the frequency domain. So somewhere, yeah, time domain and frequency domain. So what you need to remember is this one. You have to remember what is sampling, how it is defined in the time domain. And you may say that sampling is very simple, but actually there are two stories about sampling. And another one is that you have to understand the sampling procedure in the frequency domain. In order to understand in the frequency domain, you not only have to use continuous time Fourier transform, but also you have to use discrete time Fourier transform at the same time. And later, in the second half of this course, we will intensively study and use DFT, discrete Fourier transform, where we will connect not only continuous time Fourier transform, discrete time Fourier transform, but also connect them with discrete Fourier transform. So remember that. If somebody asks you, what was the most important thing you learned in digital signal processing course? You must say DFT. Because Z transform and these things, pole zero cancellation, when I was an undergraduate student, that was the topic of signal gen systems. Got it? So DFT is such an important topic. Anyway, so let's see. So this is the general case. You have a discrete time LTI system with impulse response h of n, and you have an input signal, a discrete time signal x of n. And as you know, the output is defined, or output is actually the convolution sum of these two. By the way, you remember how we define the impulse response? Already forgot? Let's say this L is a linear time invariant operator acting on the input signal. Now, what is the output? Output is the output of the operator. And what did we do? What is the most important but repeating theme in signal processing? Decomposition. So you have one signal, but you divide it into several things and rewrite this one as a linear combination or summation of these things. And here, what we use is too simple, and you may say that, what's the use of it? But anyway, x of n can be rewritten as a delayed, weighted sum of impulses, discrete time impulses. And then we recall that this linear operator acts only on the time function with time parameter, in this case, n. So using the linearity and with some leap or phase, 믿음의 점프, then we just say that, okay, let's use this infinite sums, okay. And this is constant, so it goes out of the operation. And here we go. We have what? We have the linear system's response to this delayed delta function. So we may call this as what? Impulse response, or response of the response of the linear system. So far it's linear. We have not yet used time invariance, linear system, to the impulse applied at n equals k, time k, right? If you plot this delta of n minus k as a function of n, then at time k, we have non-zero unit value and all zeros. And this one can be some signal h over n, but with a different value of k, you may have different signal. So far, let's call this or denote this signal as h sub k of n. What does that mean? This h over n is a response of the linear system to the impulse applied at time k. Then we apply what? Time invariance. Then we have what? We have this relation. So the impulse response to the response of the system to the impulse applied at time k equals the response of the system to the impulse applied at time 0 delayed by k. Again, what do? I express this simple equality verbally, right? Of course, we need for all n. Got it? Then we have this one. And for convenience, we drop that subscript 0. And it becomes the convolution sum, right? And you may say that, hey, okay, I know that. But very important. This is very, very important. And I guarantee you will see some problem related to this one with generalized version. Anyway, so I've just reviewed why we have the convolution sum of the impulse response and the input as the output of a DT LTI system. Now, let's consider the Z transform of the output signal. Why do we do that? Why? Convolution is not a simple multiplication. As you remember, in order to obtain the convolution sum for every n, what do you need? Seems that I cannot cover the sampling at all today. As this says, let's fix n. So n is fixed number. Then what is this one? With the axis for parameter k, you have x of k, the input signal, now parameterized by k, and your impulse response signal flipped and delayed by n. Then what do? You multiply term by term and then sum up. So in order to just compute this one, theoretically or in principle, you need how many complex number sums? Countably infinite, right? So if you do it in the time domain, you requires countably infinite complex number times complex number and countable infinite summation of complex numbers. In theory. Now, in order to circumvent that horrible computation, let's use Z transform of the output. So it's like this. Your main theme of signal-gen systems and this DSP, Laplace transform, Fourier transform, or any transform is this one. You somehow described your world using something. And unfortunately, computation is very, very heavy. So what do? You move to higher dimension or some different domain. There, everything's simple. And you compute something and come back. Then suddenly, your headache, heavy computation is gone. Got it? You will see this theme again and again, especially when you study discrete Fourier transform. Discrete Fourier transform allows fast computation algorithm called fast Fourier transform. By the way, discrete Fourier transform is the name of some transformation. And fast Fourier transform is what? Name of an algorithm that computes DFT very fast. What does that mean, very fast? With less computation. What does that mean by less computation? Less number of complex multiplication and less number of complex addition. Right? Simply put. So again, we do the same thing as we've done in signal-gen systems. Sometimes if we have a headache in time domain, we go to the frequency domain and do something and come back, and suddenly everything has come simple. Same thing. You want to compute the convolution, but horrible. So what you do is that you consider Z transform of your signal output, which is the convolution of two signals. And from the convolution property of Z transform, what do we have? At least the expression, the mapping rule, mapping expression for this Z transform is the product of the mapping rules. Of course, we have to be careful about what? The region of convergence. If Z is in the intersection of the ROC of H and ROC of X, then this is guaranteed. But for some Z is out of the intersection, we still have this Y of Z converging. Why? Thanks to a pole zero or pole zero cancellations. Right? So here goes some cases, but be careful. Not every, but some. Suppose we have the impulse response that is right-sided exponential signal. And you know what is the Z transform. I repeatedly told you. Now, the input is unit step with height capital A. So 0, 0, 0, A, right? Now, what is your output? As I told you, you have this problem in 수학의 정서. Believe me, you can find that. But anyway, never try to just flip and slide correlation. Let's use this one. So we know that this impulse response has Z transform, this one, with ROC. By the way, the Z transform of the impulse response of a linear LTI, time-invariant system is called the system function. And you remember this terminology used for a continuous time LTI systems too. In that case, the system function was defined as what? The Laplace transform of the continuous time impulse response. Now, we know that this signal X has Z transform and the ROC like this. And if we apply this result, temporarily putting our ROC away, then we have what? Product of these two, like this. And then we may use partial fraction expansion to have what? To have two terms. And if A has magnitude less than 1, so we have this one. If it is real, then it's kind of exponential function that is decaying to 0. Then intersection would be what? Just a second. Is it? Something's not correct. Yeah, I believe this is not correct. Anyway. Okay, intersection 1 and A. So intersection is this, correct? Okay, correct. Sorry. Anyway, so we have this one. Since this is constant, we have here. And what is this one? Same as that one. What is this one? After we take A out, this is right-sided exponentials, Z transform. So we have this result without directly computing the convolution sum. Got it? And if we plot the pole zero diagram or pole zero plot of the output, we have to work with that one, where how many zeros at the origin? 2 zeros. How many poles? 2 poles at A and 1. So we have A, in this case, it is assumed a positive real number, A and 1. And this is the reason of convergence of the output signal. Now, we have seen that partial fraction expansion is very, very powerful. When the Z transform can be written as a rational function of Z or Z inverse. Then can we generalize this one? Here goes the idea. So up there, we haven't yet said the system, DT LTI system can be describable by LCCDE. Now, let's restrict our attention to DT LTI systems with its I/O relation describable by LCCDE. And here goes the LCCDE, and you may say, what is this? Actually, you started from that one. Actually, this is very important, but too obvious, so omit it. So you have countably infinite number of equations, but when you change the parameter n, the coefficients a and b are not changing. That's why we say what? Constant coefficient, right? And they are difference equations because we can always rewrite summation as difference. And people loved differential equation, DE, so it does not say linear constant coefficient summation equation. They named difference equation. And here, except the 0th term, let's put every term on the right side by subtracting those terms. That is this one. And you divide by A0, assuming A0 is not 0. You can do that, right? Now, what do? You apply Z transform. Then what is this one? This is capital Y of Z. And this sigma and coefficient stays here. Now, what about this one? When you delay a signal, then what's the Z transform of delayed version? Z to the negative delay, right? So Z to the negative, what is the delay? K. So Z to the negative delay. And original Z transform. Now, what about these things? You have the same summation and coefficient. And here you have delayed version of the input, delayed by K. So Z to the negative delay. Again, this one and that. And what do? You collect these terms and group together. And so actually, you can directly do this. I prefer that one. See here, how many equalities do you have? Countably infinite. How many equalities do you have? You may say 1, but actually, if you vary z, uncountably infinite. But anyway, so here, this summation does not act on capital Y. So you can put a parenthesis here. And also put another parenthesis here. Then what can you do? If this is not 0 at some z, then now output Z transform, input Z transform, then what is this? This must be the system function, capital H. Got it? That is this. So even though our textbook and handouts put everything on the right side and put back, you may start from here and directly get this result. One of the reasons why I guess, textbook has this one is that sometimes this is the way to understand the current output. So this must be written as current output. And the current output is what? Is written as the past inputs and current input, linear combination of current and past inputs, and a linear combination of past outputs. Got it? So this one does not say much. It says, hey, we have linear combinations of the current and past outputs. Here we have linear combinations of current and past inputs. They are equal. But for this one, you now understand when we have LCCDE, the current output must be a finite linear combination of past outputs. If this is infinite, then it's not actually LCCDE. Also, we have finite number of current and past inputs. If it is not, we have infinite, then forget it. Got it? Precisely speaking, that is not LCCDE. Here goes another example. So Y, so output. So current output is 1 step past and 2 step past and current input, right? So this is LCCDE, not time varying. We just term by term linear transform and find the system function. And we love to factor this one from our middle school, right? Now you understand why I said that 모든 중학교, 고등학교 수학은 전자전기공학과를 가기 위해서 배운다. Now you understand this bold claim, right? So you find 1, 4, and 3 as the root of the polynomial, and you plot the pole zero plot. Got it? Anyway, another one. But without reason of convergence, you group them together as a single rational function, and then find the poles and zeros, and you consider possible reason of convergences, then you have different impulse responses. Got it? And about the causality and bible stability, you must be careful. Okay? Let me show you some strange thing. I remember I put it somewhere in the previous handout. So Probably this is the LCCDE I'm talking about. Yeah. So what is H? What is H, by the way? When you apply impulse at time 0, then your output becomes impulse response. So your impulse response satisfies this equation. Or you may consider Z transform. And you have and you may say that, hey, it's obvious. Something wrong. You are wrong. Why? Because not only this one, if I remember correctly, that one also has the same form of Z transform. So here comes something interesting thing. Here is your LCCDE. And you don't say that whether system is causal or not. Then, even though your DT LTI system, this system describes the I/O relation of a DT LTI system, you haven't yet completely specified your impulse response. It's like what you learned in physics. Probably you remember one of the pages in Halliday and Resnick showing that some steel cuts of ball throwing. So your ball, and you believe that ball moved that way, but actually that is what? Ball moved the other way, and you took pictures and rearranged it. So our physics, the Newtonian physics, does not change even we reverse the time, right? Newtonian physics. I'm not talking about thermodynamics or something, got it? Because 연력학 allows us to check which one advances and which one is not, right? So similar thing happens. And probably you remember that. Right. Because in our study on linear constant coefficient differential equation, we had the same thing. Actually, Newtonian physics with sometimes dampers and springs in physical system was described by LCCDE sometimes, right? After some approximation. And at that time, without imposing causality, we could not resolve which one is the correct order of sum up. Same thing, got it? So what I'm saying is that LCCDE itself does not resolve which HN is the impulse response. So you remember this one. But why do we love linear constant coefficient difference equation? To build real world LTI system. And in real world, we have causality. So sometimes when we use LCCDE, differential or difference, we just assume causality. That's why we don't have, in most of the cases, confusion. Which one is the actual impulse response? Got it? So be careful. Okay, let me skip. Yeah, stability and causality, not only in terms of the impulse response, but also in terms of the system response. So you remember from DT LTI system theory that a DT LTI system, the first one is that any DT LTI system can be represented by its impulse response. That is the first one, right? And second one is what? Sometimes, in terms of impulse response, we can say a lot. For example, here, causality. So, under this assumption, causality, if and only if h of n signal is causal, a causal signal. Bounded input, bounded output, stability. If Hn is absolutely summable. Right? Now, you know that the Z transform, if it exists for the impulse response, is very, very useful. Then what about checking how can we relate these two notions with the Z transform of the impulse response, which is the system function. And as we've already seen, the Z transform has what? The Z transform is a complex valued function. So if you take the absolute value, then what do you have? You have this one, right? And when do we have this inequality? Always. Got it? You have always this relation. So you can always rewrite that one, even when this blows up, right? And using the absolute value property, you have that one. And here, for Z on the unit circle, you have this is gone, then you have what? Bibo stability, right? So what is important is that this unit circle must make the summation convergent. So Bibo stability in terms of Z transform is that the ROC of Hn, Z transform, ROC of H of Z contains unit circle. Then it's Bibo stable. And also it's Fourier transformable. About causality, when we have rational Z transform, then we have this one. Why do we have that one? In order to explain that one, consider some rational function of Z. Then rational function of Z with here, the emphasis is with real coefficients. So AKs and BKs are all reals. Because when we use circuits, even though we handle complex values, we can divide by real part and unit part and cross product. So we have, when we build the linear LTI, discrete time LTI system with shift registers and multipliers, we always use real valued coefficients. So our polynomials in the numerator and denominator has real coefficients. And as you learned in high school math, even though you just memorized the result, what is the fundamental theorem of algebra? What is the fundamental theorem of algebra about the polynomial equals 0 with real coefficients? It has roots, number of roots, the same as the highest order of the polynomial, right? So it's fifth order polynomial, then you have 5 roots. Some of the roots may be complex valued, but 2 of each are conjugate pairs. That is the fundamental theorem of algebra. By using that, you can expand denominator as a product of these things. And then what does that mean? You can almost, of course, sometimes you need long division to reduce the order of the numerator lower than the order of the denominator, and then you apply partial fraction expansion, then what happens? You always have these exponential functions, especially when you have causal system. You always have some exponential function summed by another exponential function, something like that. Always. And you may say that, really? What's missing? I told you. When we focus on not just general DT LTI, but DT LTI with LCCDE, describing the input-output relation, with real coefficients, then we can always say this. Because causal exponential signals, each one has what? Reason of convergence outwards the circle. So if you intersect them, you have this claim. Got it? Anyway, this part is very confusing, and we have around 2 minutes, so let me be quick. So far, we've seen how to use Z transform to analyze some DT LTI system. Sometimes Z transform of the impulse response of the DT LTI system is very, very easily understandable by using the Z transform, especially when you compute the output, right? Now, in many cases of communications especially, our early pioneers of wireless or radio communication had a headache of interference. So Marconi, who was originally Italian national, moved toward the UK, United Kingdom, to start his venture, because Italian government and fundraisers didn't funded him enough. And at that time, the Silicon Valley was in what? Not in the US, but Silicon Valley equivalent was in the London and Britain. So he moved to Britain and got a lot of funding and started his own business, wireless communication. The problem is that he generated somehow radio wave and modulated its amplitude and possibly phase to convey the Morse code. The problem is that the other guy near him also used almost the same circuitry to generate another wireless telegram signal. And in the receiver, unintended signal also received, and suddenly his invention became useless due to a lot of interference. Then he tried to solve that one, but the problem was that at that time, he didn't have knowledge about Fourier transform or something, but he found 2 patents already filed and granted. And he combined these 2 to have new patent. Usually, such a kind of combination of 2 important patents is not accepted by a patent office, but that combination was so important, so the British Patent Office just accepted it. That becomes the British 7777, number 47, which if I remember correctly, patent. And that was this one. So it's like you have somehow use resonance so that your antenna is connected to some resonant circuit. Then this output only passes through some very narrow band signal. And here, this frequency was related to the number of oscillations of the spark gap signal. And now it's like station 1 use some signal or on this band, and another station, nearby station. Use this part, and this resonance circuit is matched to this band. Then this interference is gone. Amazing. So this entire actually signal gen systems was for the design of such a bandpass filter. Okay, so designing a bandpass filter was one of the most important tasks in early circuit theory and signal gen systems, if we call the theory as signal gen systems and circuit theory. Similarly, so this is radio communication. Now here, what we do is a little bit different, but again similar. We have a discrete time signal comes in, and we want to somehow remove, for example, some high frequency term. That kind of system is called a low pass filter. And 50-day moving average, 70-day, 120-day moving average used in stock analysis. 차티스트, 알죠? 그렇죠? 주식의 차트 이렇게 위주로 하는. Chartists use the low pass filter. And low pass filter is again so important. We are going to see some techniques to design low pass filters. But these filters are not related to the Z value. These filters are about what? The frequency, radian frequency or hertz. So it's a kind of problem in terms of frequency, F or omega, not Z. And you may say that, so far we all talked about Z transform and suddenly we go back to Fourier transform? Yes. And remember this, in Fourier transform, our frequency was a real number. But in our Z transform, our variable was a complex number. So actually, this complex number includes this real number. So we are going to solve filter design problem in a much higher dimension with two coordinates, right? In real, you had only one coordinate. Now you have real and imaginary. So it's similar to what we call in our daily lives, 한 차원 높게 생각하라. That is exactly what we are going to see in probably in this Thursday. Okay, let's stop here. There are students waiting outside.